Okay, let's start. In the last lecture, we looked at how to implement the comparator. So we started off with a basic differential pair like this, and we saw that to have a faster comparison, we need to have the positive feedback so that we have exponential growth, and that we did it by having a cross-coupled PMOS. But then we saw if we directly connect these two, we have a static power consumption. That is, even after the comparator has made the decision, there will be a path from VDD to ground that was unnecessarily consuming power. So to break that path from VDD to ground, we decided to put an NMOS here, and that also had to be cross-coupled like this. And of course, the output nodes were reset to VDD before. And same is the case with these intermediate nodes. So this is the strong arm latch, and it is one of the most commonly used latch architectures till date. And just to refresh, so if let's say the latch is active in phase 5C, the output of the strong arm latch is available only after 5C is made high. So only for half clock period it is available. So usually you follow the strong arm latch with another SR latch, so that the output is held for one whole clock period. So we then saw we can basically have this comparator, put an array of them, and form the simplest ADC, which was the flash ADC. So we took a bunch of comparators, and if it's an n-bit flash, how many comparators we need? 2 power n-1 comparators are needed, so we put all of them. So all the comparators see the same input, and the reference voltages were generated using a resistive ladder. So here at the output I'll have 2 power n-1 bits, and these were thermometric or thermometer coded bits. That is, if let us say there is a comparator here which is comparing the input with say a kth reference voltage, and let's say there is one more at k plus 1, and you'll have a whole bunch of them above and below. Say the input is lying somewhere here, so what do you think will be the output of all the comparators here? Huh? All the comparators will be 1 because input is greater than these reference levels, right? So you'll have a whole bunch of 1s here, and what can you say about the output of the comparators above? They will all be zeros. So you'll basically have a string of zeros followed by a string of 1s, and we have to convert it to a binary equivalent. And how did we do that? We basically sum up all these bits and we get the binary output. So if we have 2 power n-1 output codes here, how many bits we'll have after adding? We'll have n bits. Great. And as you can see, if I were to increase the resolution here by 1 bit, what will happen to the number of comparators needed? That will basically double approximately. So that's why it is not used for more than 6 bits or something. 6 bits, not more than 6 bits usually. But the nice thing is it is the fastest ADC we have, because just samples the input, makes a decision, and instantaneously the digital output is available. So it's a fastest ADC, and that's why it's also called flash. So we also saw how we can make a differential version. So in a differential case, the input is a differential input delta V, and we give the plus input and minus inputs as VCM plus delta V by 2 and VCM minus delta V by 2. And if the supply is from 0 to VDD, what is the range for the differential input? Yeah, from minus VDD to plus VDD. So we basically have to look this range, compare a differential input with a whole bunch of reference voltages here, and these are the differential references, say it's some Vref k, and make the decision. And being a differential circuit, even the references we have to supply in a differential manner. So let's say this is the plus reference for the kth reference. This is the minus reference voltage for the kth reference. So V ref k is the differential reference. How do we give the individual references? I mean, if you have a differential input delta V, we were feeding the inputs as VCM plus delta V by 2, VCM minus delta V by 2. Here the differential reference is Vk, so the individual things will give us, and here it is VCM minus V ref k by 2. And we also saw how we can generate these guys. So we can start off by thinking how to generate these voltages. So if we have two supplies plus VDD and minus VDD, we can basically put a bunch of resistors like this, and this will give the first, let's say V ref 1. This is a differential reference, and if you want to get half of this, so you scale this by a factor of 2 and then add VCM, and if you do that, finally the bottom one was at ground, top one was VDD. So this was the V ref plus for the first reference. Same thing you can do for the other side also, and we saw that for the minus side, this was the first reference. Right? I mean, it should also make sense, because see, if let us say if you look at a differential reference voltage of 0, so let us say this is the middle one, which is 0. If the differential reference is 0, what can you say about the individual plus and minus voltages? Equal to what? Yeah, from here, I mean, what I'm saying is V ref k is 0. If V ref is 0, what can you say about these two individually? VCM. If VCM is middle of the supply, so in this, where will I tap the output to get the VCM? VCM is VDD by 2. In this resistive ladder, where will I tap the output to get VDD by 2? Middle. So if I tap at the middle, I will get the differential reference of 0. If I had to get the first positive reference here, I will have to go up here in the positive ladder, go down here in the negative ladder, and you go in a differential manner. Great. So once you generate the references, the next job is to subtract the reference voltages from the inputs and then make the decision. If you have a single-ended case, it is straightforward. What happened? Okay, actually, this is in the last lecture actually. Okay, you can actually, I mean, from this, if you have plus and minus VDD, you can generate these, right? From this, we can actually see how we can get these. So if you have a single-ended structure, it is simple because you give V in here, V ref here. And you are set. But you have a fully differential case, so we have V in P and similarly V in M. Similarly, you have to take the difference with, let's say, plus reference for the kth and the minus reference for the kth thing, and these have to be fed to the comparator. So one input must be this, other input must be this, and we saw how we can generate these also. So if we have V in plus, if we have a capacitor charged to the reference voltage, we can basically do that. And for charging the capacitor, we did this, we connected the reference here. So in one phase we charged it to the reference, in the other phase we connected it like this, so that the signal is subtracted, and this was directly given to the input of the strong arm latch. So negative side also we have something similar. So this is V ref minus for the kth reference VCM. Great. So here, in which phase the input is getting sampled? Phase 1. So where is the input getting sampled onto, on which capacitor? Huh? I mean, input is sampled onto which capacitor here? Where is the capacitor? But this is just a capacitor acting like a voltage source, right? It is there existing only for subtracting the reference. It's basically getting sampled onto the gate capacitance here, right? And I mean, in many cases, you might not be required to add an explicit sampling cap because the gate cap itself will be large enough. But if needed, you can go and put a separate cap there, right? So we sample the input in phase 1 and say you can activate the comparator in phase 2 and will be set. So the overall flash will look like this. So you have two reference ladders, one for generating the positive reference, one for generating the negative reference. So you have the reference subtraction circuit like this. Let's say this is V in plus, you have in one phase. And basically you will go and connect it to one of the points in the resistive ladder. This is VCM. And you have a similar structure here. I will not draw it completely. And you, why are we doing this? We are, to store the reference voltage, right? We want to subtract the reference. Is that clear? Yeah. I mean, this is something I asked you guys to check out in the last class, why this should be at VCM. So I'm not going to explain. You work out and see and tell me why this should be at VCM. Okay. Please remember that we are looking at a differential input delta V. We want to compare it with a bunch of differential references, say V ref K, right? So this is what we want to do differentially. So for the positive input, we'll apply half of this. For the negative input, we'll apply negative half of this. But this is only the differential one, we have to apply a common mode on top of it. So this is what should go to here and here. So you work out and see what you get. Okay. So if we have a n-bit flash, how many such structures I need? You need 2 power n minus 1 such structures, right? And the strong arm latch we have like this, and then we have 2 power n minus 1 such structures, and the output of the strong arm latch has to go to an SR latch. And let's say you take the positive output of this and give it to an adder, and that will give the binary output. Right? So you'll have 2 power n minus 1 bits. Here you have n bits. Okay. Great. So this is the simplest flash you can make, but as such, this implementation has one issue, which is the following. So let us say you have make a 6-bit flash. How many comparators will need? 2 power 6 minus 1, which is 63. We need 63 comparators. So let us say this is the comparator 1, and let's say the last comparator is somewhere here. Okay. Now all these 63 comparators will be placed physically apart, right? No other way. And the way we have implemented it, input is getting sampled locally on each of these comparators, right? And let us say this is the clock that we are giving for the ADC. Now this clock will go here, and here it will take a long path and go there. So let us say the clock reaches here is clock 1, and this is say clock 63 or something. If let us say the clock reaching the first comparator looks like this, how do you think the clock reaching the last comparator will look like? There will obviously be some delay, so it will be slightly delayed like this. And remember that the sampling happens based on these clocks that is reaching each comparator, and let us say following it define the sampling instant. Now you see that the sampling instant is different for each comparator, right? So basically, since sampling is happening locally in each comparator, and there is a skew in these clocks, by the way this is called clock skew. Because there is skew in the clocks, the sampling instant is different for each comparator. So which means, what can you say about the signal that is being compared in each comparator? Will they be same or will they be different? Will they be different? But is that what you want? No. Remember that in flash the old principle was all comparators sample at the same time. On the same sample, all comparators must make the decision. But here that's not happening. So do you think this will be a problem for slowly varying signals or a high frequency signal? High frequency, because for slow varying signal it's doing something like this. It doesn't matter if one comparator samples here and other samples here. Okay, it's a fast signal, you might be screwed. And remember, the whole point of having the flash is to have a fast ADC. So the whole point is to digitize fast signals. So this will be a problem. And what might happen because of that is, ideally in the if you take all the 2 power n minus 1 or the 63 output bits, you expect a string of zeros and a string of ones like this, right? But now it can so happen that, let us say for this guy, the input getting sampled for this comparator might be slightly different. So it might make decision based on different input. So this by error can become 0. Others could be 1, let us say. Just giving a sample example. Okay. So this is called bubbles or sparkles for obvious reasons. And there are a bunch of ways in which you can tackle. I mean, one way is do it in the digital domain. You can clearly see that if this is the scenario, the neighboring bits are 1, obviously, which means this bit is become 0 due to some error. So we can basically go and correct it. But if the bubbles are arising due to this clock skew, there is an even simpler solution, which is the following. So notice here that this issue of clock skew is something you cannot avoid. That's simply because you have to go and route each clock. I mean, you have to go and route the clock to each comparator, and there is going to be some delay in the clocks. That is something you cannot avoid. Now the problem is happening because we are sampling the signal locally in each of these comparators, and the skewed clocks are used for sampling the signals. That is the problem. The problem is because the input is sampled locally in each of these comparators. So what do you think can be a solution for this? We have to sample it at the same time, but the sampling cannot happen here, because if it's happening here, we will be using these clocks, and these clocks are skewed. So we shouldn't sample locally. We should have a common sample and hold before everything. Okay. So what is commonly done is to have a global sample and hold or a global track and hold. This will be a simple switch and a capacitor. And of course the capacitor output cannot be given directly, so you have to buffer it. This could be a simple common source amplifier. Common drain, source follower. I mean, here you don't have to do that switch capacitor amplifier and stuff, because remember that the flash is the maximum resolution in a flash is say 6 bits. So what is the maximum signal to noise ratio? 36-37 dB. And for getting a linearity of 36-37 dB, the simple source follower is good enough. You don't need to go and put the switch capacitor amplifier and do all that business. So now this buffered signal can now go to all the strong arm latches now. So now what happens if the signal is varying? This sample and hold will sample it, and then the output of this guy will be some held signal. So I am exaggerating here. So this signal is held here. So if, let us say, one of the comparator samples at this instant, other samples at this instant, there is no error. Okay. So now, since the input is already sampled globally at somewhere, there is no point to again sample the signal locally in the locally in the strong arm latch, right? Because it's already sampled. It is not needed to again resample the signal inside the strong arm latch. That is, right now what we are doing is this, right? So we are doing this. So in one phase we are charging the capacitor to the reference voltage, say in phase 2, and in phase 1 we are connecting this to the strong arm latch like this. Remember that the signal here is V in plus minus the required reference voltage you want with the common mode shift and stuff. So this signal is getting sampled onto the gate capacitance here, but signal is already sampled, so you don't need to actually have this additional sampling switch here. You can directly go and connect. Okay. Is that clear? So if this is the case, in which clock phase I should activate the strong arm latch? Look at the circuit here. In 1, right? Is that okay? Because in phase 2 you see this is pulled to VCM. So it should be happening in phase 1. And it should make sense because see, we are feeding the signal in phase 1, which means in the sample and hold, global sample and hold, the signal is being held in phase 1. If the signal is being held in phase 1, in which phase is the signal getting sampled? In the sample and hold, the signal is being held in phase 1, right? That's why we are directly able to feed.
Yeah.
If in the sample and hold, the hold phase is phase 1, in which phase the signal is getting sampled?
2.
In clock phase 2, the sample and hold was sampling, and in clock phase 1, it is holding, and that's why we are doing this. So signal was already sampled in phase 2. We can activate the comparison in phase 1. Is that okay? Great. Now we can also do this reference subtraction in another way, a small variation to this. So here if you see this capacitor, in one phase we are charging the capacitor to the reference voltage, that is we are sampling the reference voltage onto the capacitor first, and then the input is connected here so that the input and the reference are subtracted. We can do the other way also, that is instead of charging the capacitor to the reference first, we can charge the capacitor to the input. So we can basically first sample the input here, say in phase 1, and in the other phase you can go and connect the reference here. I'll just show one half, the other half I'm not sure. This is the same thing, right? Here we are first, the capacitor is charged to reference, and when the input is applied, you have input minus reference. Here we are doing the opposite. Sorry, first we are charging the capacitor to the input. This is charged to the input. Now when you connect the reference signal to here, you will have reference minus the input here. Okay. You essentially want the input and the reference to be subtracted and fed to the input of the Stongam latch. You can do either of the two, and each one has its own pros and cons. I'll give that as an assignment for you to work. Okay. And here, in which phase I should activate the latch? Huh? In phase 1, what's happening to this guy, this node? BCM. So obviously you can't do here, you have to do it in phase 2. And it should also make sense because if you see, this is the signal. Although we have a global sample and hold, that held signal is again getting resampled locally here. So the signal is sampled locally in phase 1. So in phase 2, you go and activate the comparator. Okay. So other difference, one difference between these two is, here again, as I mentioned, the signal is locally getting sampled. So the sampling capacitor is, what is the sampling capacitor here? We are basically sampling the input on this capacitor. This is now the sampling capacitor, right? Whereas in our previous implementation, we were exploiting the gate capacitor. And in practice, it turns out we can also do the reference subtraction in a different way. So let me call it variant 1. This is variant 2. So to understand the third variant, let's actually look at a single-ended case first. So let us say you have a single-ended case where you have only V in and V ref. It is straightforward to take the difference. You can apply one input here, the other input here to the Stongam latch. And let me also draw the top portion. You have a cross-coupled NMOS here. Now let us say I call this current I1 and I2. So what does I1 minus I2 depend on? Yeah, it is GM times. I'll just say it's proportional to what voltage? Yeah. It's proportional to V in minus V ref. Is that okay? The differential input is converted to the differential current. Simple. So now we don't have a single-ended case. We have, let us say, V in plus Vref plus. So we have V in plus Vref plus. What we want is this, right? We want V in plus minus Vref plus applied to one case, V in minus and Vref minus applied to the other branch, and this has to be compared and subtracted. In a differential case, this is what you want. Now you see that I already have generated a current which is proportional to this guy, I1 minus I2. How can I generate a current proportional to this? If you take another differential pair, like this, I apply V in minus and Vref minus. Let's say the currents here are I3 and I4. So we'll have I3 minus I4 proportional to these voltages. Now basically you want to subtract these two. So which means it is basically I1 plus I4 minus I2 plus I3, right? So I1 is already flowing here, I4 is flowing here. I want to sum up these two currents. What can I do? Sorry? I'll just go and put them like this, right? So now the current flowing here is I1 plus I4. On the other side I want I2 plus I3. So I'll go and do this. Okay. So now the current flowing is I2 plus I3, and this is the differential current that will get, processed by the cross couple pair here, and then our output will regenerate properly.
You can apply both V plus Vref minus.
Where? That also you can do. That's okay. You can do any combination. Yeah. I mean, he is saying I can also apply Vref minus here, but that will not be correct, right? If you apply Vref minus here,
only one differential input I am taking, and one input is like I1 plus I4, right?
Correct.
So what is I1? V plus, and I4 belongs to Vref minus. So add these both.
How will you add the two, right? That's the question. I mean, I can't add or subtract. See, here the whole point of coming up with the circuit is to subtract the input from the reference, right? See, one difference is in the previous two implementations, the subtraction was done in the voltage domain, right? We charged the capacitor to some voltage, and the voltage was directly getting subtracted. Here the subtraction is happening in which domain? We are subtracting or adding currents. So the subtraction of reference is happening in the current domain. So again, this will have its own set of pros and cons. Again, one straight thing you can see is in all the previous implementations, so we have a switch and a capacitor like this, right? And remember that in the flash ADC we are going to have a global sample and hold. This is the global sample and hold, and then you have, let us say, a buffer like this, and this buffer is going to connect to all of these, right? And if you have a switch and a capacitor like this, in the last class we saw, right, how will the current look like in this current? The moment I close the switch, how will the current look like? Ideally it will be an impulse. In practice it will be a huge spike like this, and this current has to be provided by this guy. And remember, if you have a 6-bit flash, 63 such branches, and the spiking currents demanded by all 63 branches must be provided by this guy. But the moment you do the subtraction of reference in current, you no longer have any switch or capacitors here. The input is directly fed to the gate, reference is directly fed to the gate, right? So here you will not have this, you will directly have the gates connected, and this will be much easier to drive, right? But of course, the problem is, now you see that the reference voltages are directly connected to the gate. Now we want the NMOS to be on, so which means you can't apply a very small reference voltage here. So that sort of limits its usage also. And also, we can't apply. I mean, this is reference voltage is VCM plus or minus some Vref k by 2, right? So the lowest side is some VCM minus the lowest reference by 2. Right? So you cannot apply a very small reference here, that might turn off this guy. And also, if you see here, ideally we want input to be applied as VCM plus a delta V by 2, and this guy is the same VCM plus kth reference by 2. Now here we have assumed the both common modes to be same, right? But if they are not same, that could happen because the input is coming from previous stage. Let us say there is an error in the common mode. This might have a delta VCM here, let us say. Now the comparator will make decision based on these guys. Instead of comparing delta V by 2 with Vref k by 2, it will compare delta V by 2 plus delta VCM with this. So it also requires very tight matching on the common modes of these parts. Okay. Great. So now we have seen simple flash ADC. So use a band gap reference. You have to use a band gap reference, or I mean, if you want really tight, or you should have an LDO. Correct. Okay, I mean, I'm saying the simplest, I mean, one way if you are doing the reference subtraction in the voltage domain, you generate using a resistive ladder like this. Mismatch in the resistor, so you have to size them accordingly. That's all. That's all. Yeah. I mean, the one nice thing about flash ADCs, you don't require very tight specs on linearity, right? Yeah, you got 36 or 37 bits maximum, 6 bits. This much of resolution, this much of thing can be obtained easily with resistive. So now we have seen flash. Let's actually look at some of the non-idealities we can have here. Right? And remember, in the flash, the only thing that is there is the comparator. So let's see what are the non-idealities we can have in the comparator. So when we looked at the op-amp non-idealities in the switch capacitor circuits, what are the non-idealities we considered? Yeah, first we looked at offset, and by extension the flicker noise, and yeah, we looked at the finite DC gain, and we also looked at thermal noise, how to analyze thermal noise. So we'll do the same for the comparator also. Now, yeah, for a comparator we'll see what offset does, and first we'll see what DC gain maps to in a comparator. And thermal noise for a comparator is slightly more involved, so we'll not consider here. Because you see, if you have a strong arm latch, the transistors operate in all different regions, like cutoff, linear, saturation. It's getting on, getting off. So it's not an LTI network, so it's slightly out of the scope of this course. I'll not cover here. Yeah, one thing I want to highlight here is that, see, these two guys, they're not something fundamental. You can think of it as some imperfections in practice. So we can come up with techniques to greatly reduce the effects of these. And in fact, we did see some circuits that can help us combat offset and DC gain. On the other hand, thermal noise is something fundamental. It comes straight from thermodynamics. Because of non-zero temperature, it reduces thermal noise. That is something you cannot prevent. Okay? So you can't do a lot with thermal noise. Only thing you can do is understand how to analyze the effect of thermal noise on your circuit, and you should know how to calculate the noise power in your circuit in terms of your circuit components. So you can design your circuit such that you meet the required noise performance. That's the only thing you can do. You can't do a lot to reduce this. So let's start with offset for comparator. So what does offset mean for a comparator? So ideally, let us say the comparator must behave like this. When the input is 0, the output must become VDD, right? And if the input is less than 0, it is 0. But with an offset, what do you think will happen? There will be a shift in the characteristics, either to the left or to the right or anywhere. And just to again emphasize, the offset is a random quantity. So if we take 1000 identical comparators, all 1000 ideally, let us say, must have the threshold to be 0. Now, due to this offset, you will have different threshold voltages for each comparators. All 1000 comparators will have different thresholds, but for a given comparator, it is constant. And if you plot the probability distribution of this offset voltage for all the 1000 comparators, what distribution do you think it will take? Central limit theorem, so it's all Gaussian, and the mean of this will be 0, because in practice we all have only zero mean processes. So as long as we have offset arising due to random issues, the mean will be 0. So first let's see what happens if we have an offset, right? I mean, let's see if this is even an issue in our flash ADC. If it's not an issue, we don't have to worry, right? So remember, we are now looking at a flash ADC. So we have a bunch of comparators. Now let us say all the comparators are ideal, they have zero offset. Then if I plot the input output characteristics of this ADC, how will it look like? No, it's a flash ADC. How will it look like? Huh? It will be a step, right? It will be an ideal step characteristics like this. And these are the reference voltages against which each each comparator is comparing the input with. Fine. This is the case when there is no offset, but if there is offset, what will happen? Yeah, and remember that each comparator has different offset, right? So which means, let's say the first comparator, instead of comparing it with this voltage, it might compare it with this. Let's say second one does this, third one does this or something. So now you see that the switching, or the comparison voltages are all distorted. So what will happen because of this? So we'll basically we saw DNL INL, so this will straight away result in non-linearity. So this is going to be a problem, so let's see how we can address it. Okay. And there are different schools of thought for this. The first thing is to actually notice where this offset comes about. So this offset is coming because we have, in our comparator, we have a differential structure like this. Let's say we have a whole bunch of them at the top also. Right? I'll probably draw the NMOS here. I'll also draw the PMOS. Let's finish the circuit. Now we have basically two differential halves, and we have always assumed that the two halves are identical. That is, this guy is identical to this transistor is identical to this, and so on. But in practice, no two things are identical. There will be some mismatch. This could be mismatches in the threshold voltage of transistors, mismatch in the device sizes, mismatch in the mobility, and so on. So if there is a mismatch, what will happen is this. Let us say I apply the same input V to both inputs. Ideally, if there is no mismatch, both these halves are identical. So what can you say about the two outputs here? They will be same. In fact, for a zero input, comparator's output is not defined, right? But if there is a mismatch, so let us say this guy has some threshold of VTH, this has a slightly smaller threshold. If I apply the same input, what can you say about the two currents? I1 will be greater than I2, and that will obviously result in difference in these two voltages, and the difference will get regenerated, and the output will reach VDD or ground, whatever, right? So what can happen is, even when the input is 0, you can have the output to be VDD, and your characteristics will look like this. And it turns out that if you take any two transistors which are supposed to be identical, you know that there is going to be some mismatch in each of these properties, and the standard deviation in this mismatch is inversely proportional to the square root of the area. Okay. So this is called Pilgrim's model or Pilgrim's law. Just directly give the result. And at least in a strong arm latch, it turns out that the major contribution for this offset is this guy. Remember that you also will have mismatches due to these transistors, but in a strong arm latch, it turns out the dominant contributor to the mismatch or the offset is the main differential pair. Okay. So if you actually look at the standard deviation of this offset for the strong arm latch, it will be inversely proportional to the area of the diff pair. This is an approximation because I'm ignoring offsets of these, they are negligible. To a large extent, the offset will be dependent only on these guys, right? So this should give one starting point. So what I can do is, I can choose my differential pair sizes so that I can get reasonable mismatch for the offset. Okay. So in practice, from your linearity specification, you know what should be the standard deviation of your offset voltages. From this, you can actually find what is the appropriate size for the differential pair. And in practice, this proportionality constant, and remember that this I can write as some a by root of WL. Right? This proportionality constant is not known to you, directly. So you'll have to do one experiment or one simulation and find out what this is. You can take a simple differential pair, or let us say you make a comparator like this, and you run simulations to find out what this proportionality factor is roughly. And for running this, you have to include the mismatch in the devices. And I think I cross coupled it wrongly. Yeah. And these simulations are called Monte Carlo simulations. Have you heard of this Monte Carlo somewhere? Okay. Basically, any kind of analysis or simulation, including statistical randomness, it's called Monte Carlo. So here the randomness is basically mismatch in these guys. So you run a Monte Carlo simulation. Let's say you run it for 100 or 200 different times. You'll have 200 or 100 different offset voltages. Find the standard deviation of it. From that, we can find what is this proportionality constant, and then you can back calculate what is the reasonable area for my differential. This is the starting point for your design, or at least one starting point. You size your differential pair based on the required sigma of the offset. Okay. But sometimes you might find that, let's say your specification is very stringent, or let us say in your process there is a lot of mismatch, then the required device area might be unrealistically large, right? I mean, let us say if I keep increasing the size of these guys, what will happen? So capacitance here increases. So what happens? Huh? Not delay. I mean, if you think about it, where is this guy? I have it somewhere here. Remember that this is all getting driven by simple buffer here. The load for this guy will keep increasing, which means this will have to burn more power. Sometimes you might find that if you can't exactly size to meet the required specification for your mismatch, but you do start with a reasonable size, right? And if you're not able to meet the required sigma, yeah, to some extent, yes, that is true. Yeah, because I mean, basically, it's all switching current, right? Yeah, but the thing is, if you think about it, initially the working of the strong arm latch is such that there is no path from VDD. Initially, only these nodes will discharge. It's just an inverter, but you're not increasing the size of these guys. You're not increasing the size of these guys, right? See, in the strong arm latch, initially only these two nodes start to discharge, and then these two nodes start to discharge, and then the PMOS turns on. So if you increase the size of these NMOS devices, initially you will be allowing a lot of current, and the currents are pulled out of these capacitors. You are not pulling out of VDD. Yeah. Is that okay? Please recollect, in your strong arm latch, the operation is such that first the differential pair is the only thing that is on, because you would have reset all these nodes to VDD. Only the differential pair will be first on. After the differential pair is on, these voltages will start to drop, let us say P and Q, and once P and Q start to drop beyond some voltage, these NMOS transistors will turn on, and once those NMOS transistors turn on, the output nodes will start to discharge, and only after the output start to discharge, the PMOS turns on, and only after PMOS turns on, you have the regeneration. Okay.
There is no harm in increasing the size of the
It is not no harm. That's what power will increase, but
power in the buffer will increase, but Other than that, in the
Here also the power will increase, but I cannot say that it will double if you double the size of this.
there is, the speed that we get
Will be higher.
will be very high, and the power that we will be using only in this will
Might not be so much. This is my understanding. Yeah.
So in that sense, it will be beneficial.
Yeah. Okay. Great. So as I mentioned, you start with this, but let us say you are not able to meet the required condition. You can do other things that we'll see. So second thing that you can do for correcting offset is this. Now as usual, we'll model the offset in the latch as this. We'll assume that the latch itself is harmless. There is no offset. The offset is there because there is some hypothetical voltage source added. Right? So ideally, let us say this is V in, this is VOS. Without offset, if input is greater than 0, the output would have switched to VDD. But now what is the input that is going into the latch?
V plus VOS.
That okay? V plus VOS is what is given to the comparator. Only if this is greater than 0, we'll have the decision switch to VDD. So if I plot this, it will look something like this, right? So here it will be 0, right? And to give some numbers, let's say this is 1.2 volt, say the offset is some 5 millivolts. So now here, do you think the comparator will make a wrong decision when the magnitude of the input is large or when the magnitude of the input is small? Small, right? If the magnitude is large, you will be lying somewhere here or here, the decision is fine. Only if you are in this region, 0 to minus 5 millivolt is when it is making wrong decision, right? So now you know that if we have an offset, if I give a small input directly to the comparator, that is going to be creating issues. But if the input is indeed larger, it's okay. But I want to compare a very small input, but I can't apply the small input directly. I know if I apply a large input, it is okay. So what can I do?
VCM.
What VCM?
Put something, make it.
We can basically amplify it, right? Isn't it? I mean, the logic is, I know that if the input difference, sorry, went off. The logic is this, right? If I know that if the differential input given to the comparator is large enough, the offset will not create a lot of issue. So you basically go and amplify this upfront. So now, if this is V in, what is the signal? A times V in. So what is the actual signal that is compared by the comparator? Plus VOS. So only if this is greater than 0, it will toggle. So what is the effective offset we get now? Fine. So if I basically put it in a box and sell it to you, you will infer that this is a latch or a comparator with an effective offset of minus VOS by A. Right? But do you think this is okay, or could there be some other issue here? How are you going to realize this amplifier? Great, differential pair. Why was there an offset in the latch in the first place? There was a mismatch in the differential pair. Now we are using another differential pair. So this itself will have an offset, right? You can't directly go and use it. We'll have to correct for this offset first, and only then you can use it. Okay. And it's okay because we kind of saw how to correct for offset in amplifiers, but those were for closed loop switch capacitor circuits. Here we are using in open loop, but similar principles can be extended. So again, the logic is same. I'll show a single-ended case. So here there is an offset voltage, right? Now in principle, if I can put a voltage source here, the same polarity is okay. So I don't have voltage source. What do? I put a capacitor charged to that offset. Now the second question is, how do I obtain a voltage equal to the offset of this guy? You put it in unity feedback like this. So the overall circuit will look like this, right? So you have this guy. So in one phase you go and do this. In phase 1 you do this so that it is charged. In phase 2 you directly apply the input. Fine. If I were to draw a fully differential case, it will look like this. Let's say this is minus plus. So again, same thing, in one phase you go and put it in unity feedback. Let's say that is in phase 1. And in that phase you want the capacitor to be charged to this offset, you connect the bottom plate to ground. And in the other phase you connect the input so that the input is getting subtracted from the estimated offset and that is directly given. So this can be then given to a strong arm latch. And yeah, fine. Now it turns out using this amplifier, by the way, this amplifier that is used before these latch is called preamplifier. It turns out using this preamplifier will help us in one other aspect, which is basically the second non-ideality that we wanted to discuss, which was DC gain. Now let's see what does DC gain mean for a comparator. Right? Now we know that if we have a differential input delta V fed to the comparator, the output rises exponentially. That's the whole point of having this regeneration business. So if I apply a delta V, let's say delta V1, the output will be something like this. So it will start here, by exponential increase and set to VDD. Now let us say I take another input delta V2. Delta V2 is smaller than delta V1. That will also increase exponentially, but will it increase faster or slower? It will be slower. Is it okay? I mean, this is delta, it's delta V2 times e power t by tau, right?
You want it to be, yeah.
So it will rise slower like this. Okay. So now which means if let us say my time available for comparison is small, or if the input is really small, let us say this marks the end of comparison. At the end of the comparison phase, the output of the comparator has not reached a valid logic level, right? So it is stuck in between. What is this called? Have you seen in digital circuits? No? Huh? Okay, it's called metastability. Have you heard this term before? It's common in digital, right? So it means that the output has not reached a valid logic level. So now basically now you are dependent on the succeeding digital logic and the random circuit noise, and that will only make it go to either 1 or 0, and you will have an error because of this. Again here if you see, you think the problem will happen if the input is small or if the input is large. Only for very small inputs you have this issue. So if I, instead of applying the small input directly to the comparator, I can do the same thing, I can amplify it. So this preamplifier will also help in that, right? So it helps in both offset and metastability. So one fine point here, see here the strong arm latch that we are using, do you think does it have a static power consumption? No, right? It's a truly dynamic circuit. I mean, in fact, we came up with the strong arm latch with the motivation for removing the static power consumption. So this is a truly dynamic circuit. So which means if this is the clock, when will it consume power? Only at the rising and falling edges it is going to consume power. But now this I mean the latch itself is dynamic. Now for this preamplifier, if you go and put your textbook differential pair like this, it will have static power consumption that completely defeats the purpose, right? We started with the dynamic circuit, but to solve some problem we went and put a amplifier that is consuming power all the time. So because of this we don't use static amplifiers here. We use one of the dynamic amplifiers that we kind of discussed in the last Saturday. So and one commonly used guy is this. I just mentioned it in the end of last Saturday. I'll just show it again. Yeah, I'll just draw it once. Yeah, exactly. So let us say this is phi bar and phi, or let's say phi amplification. So phi A, phi A. I mean, basically I have switches connected to VDD. So how will I realize the switches? PMOS. So I'll go and put a PMOS. And what will be the control for the PMOS? phi A, right? So I'll replace both these guys with the PMOS, clocked at phi A. Now notice that at the output you are going to have parasitic capacitors. So let us say here apply VCM plus delta V by 2. So let us say when phi A is 0, if I call it X and Y, what happens to X and Y? When phi A is 0, what happens to the transistors? So these are on, this guy is off. So what happens? The nodes outputs X and Y, those nodes are pre-charged to VDD. So they will be at VDD. And let us say at this point, phi A is made high. Now what will happen? What about these transistors first? They will be off and this will be on, right? So essentially the circuit will look like this. You will basically have the parasitic capacitors at the output and then the differential pair here, right? And I am applying the inputs like this: VCM plus delta V by 2, VCM minus delta V by 2. So what will be the small signal current flowing in this transistor? I am applying delta V by 2, so it's GM delta V by 2. So if I say this is I1 and I2, I1 will have a DC plus GM delta V by 2. What about I2? So we basically assume that delta V is constant. So this current is also constant. We are pulling constant current out of these two capacitors. What will happen? They'll drop linearly, and which will drop faster? This is X, Y. X will drop faster, so one will do this. Will do this. Now again, we can also write the expression. So let us say Vx. What is Vx? How can I write the expression for Vx? VDD minus let's say this capacitor is C. It is I1 by C times T, and I also know I1. Let me replace that. I1 is that DC current I0 plus GM delta V by 2 by C times T. Similarly, Vy is the other thing. So if I look at Vx minus Vy, what do I get? GM by C T times. Fine. So as you see here, as time progresses, the difference in the output also keeps increasing. That is apparent here, right? So let us say this is the end of the amplification phase. Let us say this is some T0. This is the final output difference we get. So what is the final output I will have? GM by C. And what is the final gain I have? This is the gain, right? So
this gain is I enough as a normal.
you can actually get very high gain. Remember, this is we are looking at a parasitic capacitor. Yeah, you can have a very small capacitor, and then if you wait long enough, and if you have a large enough GM, you can actually get easily of 10, gain of even 10. It's not possible. I mean, it's not impossible. And in fact, people do that all the time. Okay, so this is a dynamic amplifier, and in this case, when are we drawing the current from the supply? Remember, when phi A is 0, that is when VDD is even connected to the circuit, and this is the connection we have, and this part is off. So we are only drawing current from VDD to charge these capacitors to ground. So these capacitors to VDD, right? So this is again a truly dynamic circuit, and this kind of dynamic amplifier is what is commonly used. Okay. But one thing is, see here, if I have this kind of dynamic circuit, I can't go and do this kind of offset correction simply because here you see that the gain of the circuit changes with time, right? As I wait for longer and longer time, the gain increases. In fact, the gain is increasing with time, right? Here you can see. Okay, so you can't use conventional techniques that are that work for static op amps. We'll see what can be done for correcting the offset of these dynamic amplifiers. But before that, if you see here, I have applied a constant input delta V. Output is going as a ramp. What other block do you think will give a ramp output for a constant input? what is some other block? I mean, what is a block that gives a constantly increasing ramp output for a constant input? It's an integrator, right? So in fact, this is basically an open loop integrator, okay, and sometimes it's also called as dynamic integrator or whatever, right? So in practice, for the preamplifier, we always use a dynamic amplifier like this, or the floating inverter structure that we discussed in the last class, or any of them. But the thing is, we can't correct for its offset directly in this manner. So we'll see how offset of this guy can be corrected, and the same offset correction can be used for correcting offset of this also actually. So that brings us to the third option for offset correction, which is calibration. This is the simplest among everything. The principle behind this calibration is pretty simple. We know that in all our circuits, the main culprit for creating mismatch or offset is the differential pair, right? Let it be the dynamic amplifier, let it be the strong arm latch. You always have this differential pair, and then you have things connected at the top. Now we are having mismatches between these two guys. So which means even if I apply the same input to the two transistors, the currents in these two branches are not same, right? Now if I can somehow make the currents in these two branches identical for the same input, we are okay, right? So what is done is this. I'll erase this. Let us say, in addition to this differential pair, you have an array of NMOS transistors like this. Okay. Let us say this has a W size W. You can have this to be W0 to W0 and so on in a binary weighted fashion, and W0 can be smaller than W. Let us say. Okay, and let us say you all the gates are connected to the same, by the way. You put appropriate number of them in parallel and connect it to your main circuit, and you do that in either sides. Again, all gates are connected, and this is just one brute force way. Now we know that we are going to have, when we didn't have this, the currents in these two branches were not identical. One of them, let us say, the left side current was higher than the right side current. Now what you can do, you can go and put additional transistors here with small widths, so that the current in this branch is increased. It's essentially going and correcting the offset itself, correcting the root cause of mismatch itself. Is that clear? Basically, the issue of mismatch was when we applied the same input here, the currents were not equal, right? Now you try to make the currents equal by countering the mismatch. Now let us say when we didn't do this, the right side was stronger. That is, for the same input, the current flowing in the left side branch was stronger. So for the same input, say the current in the left side branch was greater than the current in the right side branch. Now what you do, you go and add additional transistors here that will pump in more current in the right side branch, and that will try to correct for the mismatch in the current. Is that logic okay? The point is, you somehow add additional stuff on one of the sides or on both sides to make both sides equal. This is like taking the weighing balance, right? I don't know, old times we have vegetables put on one side, people put different weights and try to balance the two, right? Similar logic. This is the simplest one you can do. It's not necessary that you have to put additional transistors here. You have to introduce counter balance in one of the branches somehow or the other. Okay, sometimes you might find that the main issue is because you have asymmetrical loading at the output side. Let us say the mismatch is coming because this is some C, this is some C plus delta C at the output of this strong arm latch. We can go and put an array of capacitors here on either sides and put appropriate number of them in parallel and go and connect it. That depends on that depends on your application. You know what is the final sigma offset you want. You can't exactly correct, right? You will correct it with some error. You make sure that after correcting, that residual error is okay for your specification. This is the simplest brute force way you can do, and this is the most commonly done in practice now. And you'll find in almost all analog and mixed signal circuits, this notion of digital calibration is very common. Basically, the idea is to tackle any analog imperfections using some digital circuits like this. I mean, here basically all you need to know is how many transistors I need to connect here. It's simply a matter of the controls for these switches, right? It's essentially a digital logic. Here, anyways, it's a comparator. Outputs are digital. You look at the digital output, have some logic that finds if you have mismatch or not. If you have mismatch, you go on and turn on switches here that will put transistors in parallel and see if it's correct. Is that okay? So in practice, this is what is done. So you always have a preamplifier in front of your strong arm latch or any latch. I mean, not always, but if you want, you can have. And as I mentioned, this preamplifier helps in suppressing the offset of this guy and also in reducing the metastability. And this is always a dynamic preamplifier, could be the integrator we saw or the floating inverter structure.
preamplifier mismatch. So if we are increasing the size on one side, just increasing the other, basically this changes the load of the preamplifier. That's the load of the preamplifier.
Yeah, okay, I understand. So in that case, what you can do is, I mean, he's saying if you add transistors here, one side becomes stronger than the other. So the gate capacitance on one side will be larger than the other. That will present asymmetric loads. Yeah, like I mentioned, this is not the only way, right? The other way to counter this is, let us say you have this, you don't touch the gate side. See, remember that I just want to make these two currents equal, right? And if I apply say V, remember that this voltage is converted to the current through the transconductance of the transistors. You just need to change the transconductance. One common thing that is done is to put a bunch of resistors here. You basically go and add a source degeneration resistor, and the moment you add a source degeneration resistor, the GM will also change. You put the appropriate number of them in parallel and connect. This is what is commonly done. Okay. But I was just giving an example. The underlying principle is you go and correct for the mismatches by counterbalancing the error you have. That's all.
So, you are saying that we are connecting many transistors, many capacitors, and many resistors in our required configuration, and
Correct.
according to the application, we are turning on and off required transistors.
Yeah. That's all.
Make that particular.
Exactly. You don't have to do everything. You don't need to have array of resistors, array of capacitors, array of transistors. One of them is enough. And this is one of the most commonly done things. Because as he mentioned, if you put different transistors in parallel, now in one side the number of transistors might be larger than the other, which means the gate capacitance on one side is larger than the other. That will present asymmetric load to the previous stage, right? So the common way to tackle it is using this thing. Okay. So you put this, and here you have the tail transistor. So you either have a strong arm latch directly like this, and you do this calibration here to correct for its offset, or you can put a preamplifier here, and this preamplifier is always a dynamic amplifier, and then you can do calibration for both. This is the common technique that is adopted. Is that okay? I just want to mention one more thing about offset.
So, if we calibrate it in preamplifier,
Right.
so we don't need to calibrate in another set of strong.
That depends, right? Let us say if the preamplifier is providing enough gain that offset of this guy is suppressed a lot, it's okay. But let us say even after adding the preamplifier, the offset in strong arm latch is significant, then you have to do calibration here also.
If we are doing calibration there, so
See,
what is the point of doing calibration?
Yeah. See, the point of adding the preamplifier is to make sure that the offset of the strong arm latch itself is reduced when you look here, right? Now, when you add an amplifier here, you have to correct for its offset, and for correcting its offset, you first calibrate this guy. Now you don't have to worry about offset of this guy. The offset is, let's say, dominated by finally offset of this guy divided by the gain A. Fine. Great. So one last thing about offset, interesting thing. So now we know that if we have a strong arm latch like this, there is going to be some offset, right? So instead of the output switching at 0, if I apply, let us say, V in plus and V in minus, ideally you want the comparator to look if V in plus minus V in minus is greater than 0. If there is an offset, let us say it is comparing with some offset voltage here, this is 0. Fine. So now what it is doing, it is checking if V in plus minus V in minus is greater than some offset voltage. Right? That's what is happening. Now remember that in our flash ADC, we are having a whole bunch of comparators, and our goal is to check if V in plus and V in plus minus V in minus is greater than any reference voltage. I will call it VRK. This is what you want in flash ADC. You have, let us say, 2 power n minus 1 reference voltages. Each input is, the input is compared with each of these reference voltages. Right? So now the thought process is this, right? Anyways, I know that with mismatch, I am going to have this. Why can't I somehow choose my offset voltage so that the offset voltage is equal to the reference voltage I want in the flash? Right? So of course the inherent offset might not be good enough. So you go and introduce offset yourself. Right?
That's more tougher, right? Because now we need VREF.
No, you don't need VREF. That's what I'm getting at. Let's follow the thought process, right? So now we introduce offset following the same procedure that we saw, right? So you put a bunch of resistors here, connect appropriate number of them in parallel on either sides, and that will introduce offset. So now you can basically choose the correct number of resistors so that approximately this offset is equal to one of your reference voltage. Then you see, you don't need to generate reference voltage. Earlier we had to generate the reference voltage using a resistive ladder. Now you don't have to generate reference voltage because you are exploiting the inherent offset in this differential pair. Second, you don't have to subtract the reference voltage from the input, right? Because we are directly applying the input here. The offset itself is there, and that itself is getting compared inherently, right? So this is one thing that is commonly done. So what you have is a bunch of comparators, and this only the input is applied, and inside this you have, let us say, a bunch of resistors, and in each comparator you choose the appropriate number of resistors in parallel, so that in the first comparator it is some VR1, here it is some VRK, and so on. The offset in each comparator must be programmed appropriately so that the input is compared with the required reference voltage in each. If you do that, then you don't need to generate the reference at all. You don't need to subtract the reference from the input explicitly. It all happens in the circuit itself. So this is another thing that is also done. And this is basically a circuit example of, if life throws lemons at you, what do? What is the saying? If life throws lemons at you? Okay. Make lemon rice. Yeah. And it's basically selling the bug in the circuit as a feature, right? It's a life lesson also. An egg breaks, don't worry, make an omelette and eat. So let's stop here. We'll continue.